Welcome to today's webinar. The topic today is geotechnical analysis of pile foundations in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the technical content of the website, the German and English webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Alexander Meyerhofer. The presenter will be Juliane Stopper-Akdak. She's responsible for customer support, and she's the main responsible person for the add-on geotechnical analysis. Alexander, who will support me, as I said, by answering the questions. He is the head of product engineering concrete, and he works also in the customer support. For the attendees who participate the first time, I will say something how you can ask questions. At first, I switch off my camera that you can see the full screen. Just press that button with the question mark, then enter your question in that field, press send, and then we will get or receive your question, and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Juliane. Juliane, it's your turn.
Okay, then thank you very much, Andreas, for the introduction. You should see now my screen, and we switch to the next slide. Here we can see the agenda for today's webinar. We will, in a first step, create a single pile model. This shall work as introduction into the piles in Rfem 6. We will define the pile input together, and we will discuss the calibration for piles in finite element analysis with load displacement curve. After that, we can come to the next part of the webinar. We will have a look at a bridge foundation. It's a pile foundation, of course, and we will have a look at the model and the analysis, and we will work with the results and create a printout report for this. In the third step, we will speak about prospects for the add-on geotechnical analysis. I would like to speak about the projects we are currently working on, and I would like to tell you which steps, which features will follow next for geotechnical analysis. Okay, then we can come to the first step. We go to the introduction. If you have the geotechnical analysis add-on, it provides the member type pile to you in Rfem 6. The pile resistances, the skin friction and the base resistance, they can be defined with strength and stiffness. And the piles, this is info, the piles are 1D structural objects connected to the 3D soil solid elements, and they are connected via releases that are able to represent the pile's shaft and base resistance behavior. And how the values can be defined is provided on this slide. You can take the E modulus from the surrounding soil. This means for more Coulomb model, you would take the primary loading E modulus, and if it is the hardening soil model, you would use the unloading and reloading E modulus, EUR. And with this E modulus and the Poisson value, you would be able to calculate the related shear modulus. And the shaft resistance and base resistance, they can be calculated from the shear modulus is provided in these equations. And these equations are a first value for your input for your pile. then the pile's behavior can be calibrated with the known load displacement curve from field tests or standards. So if you have a project, you have either field tests or you would consider a known load displacement curve from experience, and you can calibrate your single pile model. You can calibrate your pile in a single pile model so that it reaches the load displacement curve you expect or you would need for your project. And if your single pile model can represent this load displacement curve, then you can use this pile with this input in your main model with more piles then. Yes, and we will do this. I have prepared this example. Well, I haven't prepared the example, but we use this example. It's known from the literature, and the slides I'm currently showing to you, they are provided in the download on the website for this webinar. And in this literature, you can find a deeper description for this project. And there is a pile load tests done in this LZ Bridge project. And this curve was received, and our aim now is to reach a load displacement curve that fits to this of the literature. Yes, and the shear strength and shear stiffness and the axial strength and stiffness was calculated, and then it was put into the Rfem, and we received the load displacement curve, and this model we will now create together. So therefore we go to Rfem now. I just open Rfem, and we, via this button, create a new model. We will get to the base data where we can give it a name. I will call it single pile model. And yeah, that's it. We can now go to the next register, to the add-ons, and here it is required to activate the geotechnical analysis add-on, which you find here in the special solutions, and we also need the construction stages analysis. Yes, with activating these add-ons, our main program, the finite element analysis program Rfem, gets these add-ons input options integrated, and also the analysis, and you will also have the output then in the main program. So these add-ons, they are directly integrated into the main program. You can work in the main window, which is a good thing. It's more easy to have a good overview on your model. Okay, so now we have an empty model prepared, and I would like to delete all unassigned basic objects. It's like this Rfem keeps, let's say, in mind which objects you used in your last models, and then it provides these in a new model because you might use similar materials or sections or something. But I want to start from scratch, that's why I did delete them. Okay, now we can come to the material. I do a double click here and come to the material dialog, and we will in a first step define a concrete. I will take C30, 37. We can maybe change the standard. Yeah, we take this one just for the start. I can go on apply, and I want to make it user defined as I want to change some values. The specific weight is reduced in this example as it is a 1D object, and in the area where the cross section actually would be placed of that pile, there is a soil material placed. And this soil material already has weight, so as they overlap the cross-section of the pile and the soil safe weight, we put here a smaller weight so that the sum is the right value. I go on apply, and I also change the E modulus as it was defined in the literature for this single pile test. Okay, then I have the concrete prepared, and I would like to create the soil now. I have the Alzey bridge soil. I call it like this as the project was named like this. The Alzey bridge soil. And if you have soil, you have to change your material type to soil for receiving the specific soil material models here in the material models menu. We will use today the modified hardening soil model, so I activate it, and in this base register I can define the weight. I have the drained specific weight here and the saturated specific weight here. Okay, and then I can come to the specific register for this soil material, and I would like to define the material values for the soil now. I would like to change the units, and this you can do in our dialogues via this button here. I would like to have here kilonewton per meter square for the E modulus and also for the strengths. Okay, so now for the cohesive strength we would have 20 kilonewton per meter square, and a friction angle of 20 degrees is was found in that soil of that project. We have P reference, it's the reference stress for the stiffness of 100 kilonewton per meter square, and this power here is 1. The oedometric primary loading stiffness is 27,150 kilonewton per meter square, and the shear hardening parameter shall be 6.9. The stiffness of at reference stress for unloading and reloading is 90,000 kilonewton per meter square, and the Poisson's ratio is 0.2. And we have a pre-overburden pressure of 50 kilonewton per meter square. I say okay, and my materials are defined in that model. Now I can come to the cross section of the pile. As our pile is made of concrete, we have it, as we have defined as a first model material, the concrete, it is selected here. You could also define here a new model material or take one from the library, but for us this is perfect. Then we have a circular cross section, so I can select it here. We have here several cross sections provided that are more often used, and you can directly in here define the diameter. You could also you can define it in the name. You could also find it here, but this is fine for us. It shall be 1.30 meters in this example. So I have my pile defined. That's it for the basic objects in this model. We don't need any further settings here. We can come to the geotechnical analysis settings. So the first point we want to define is the boreholes here. I do a double click and we come to the dialog. The boreholes dialog is for defining the soil stratigraphy that was found for this location. Here we keep the 0 coordinates. Then we can define the groundwater. I will show again what we had. We can see here we had groundwater and was 3.50 meters below ground level. We have a pile length of 9.50 meters. We have 19 meters of soil in the depth and 26 meters of soil in the width. So we can come back to our model and we can define it. We have here 3.50 meters. And we have only one soil layer in this test, and it is 19 meters. Oops. I say OK, and we have our soil defined here. Then we can come to the soil massif. I want to create a new soil massif. Here I assign my borehole, and I have a soil massif that will be generated from boreholes. The center of the massif can stay here, only I have to give the size of 26 meters. And I can, in the options, activate my groundwater, so the groundwater level will be considered. This soil massif helps us to generate the soil solids that we need, and with agreeing with say OK, now my soil solid is generated. We can have a look to the basic objects and see what was generated. We have a soil generated, we have the boundary surfaces, and we have the groundwater level surface. And we have here, we can see in types for surfaces, we have also the surface supports. I want to delete these one, they are not needed in this model. These are the one of the soil solid. So I want to have a short look on this display navigator. Here you can do a lot of settings regarding the display, and I would like to see the colors of my soil dependent from the object property. This looks better for me, and I would like to not have the surface supports shown, so I do a click here, and I don't want to see the borehole any longer. I don't need this right now. It's still in the model, it's only not displayed because I want to place my pile there then. Okay, then we can come back to the data and we define our third geotechnical analysis object. We define the pile resistance. So I do click on new pile resistance type, and I will show you one thing. This is a table I prepared where I did calculate the input data with the equations that were shown on the slide. I did put here the unloading, reloading E modulus. The shear modulus is automatically calculated from that, and with the Poisson's ratio. And these are the shear strength and shear stiffnesses, axial strength and axial stiffness, and I can now give it as input to my model. We have here 49.31 and 49.31, and I have here 18.7500 as shear stiffness for the shaft, and I have as axial strength 994.48 kilonewton per meter square, and we have 12,187.5 kilonewton per meters. I say OK, and I have this prepared in my model. Now I can define the pile. I would like to do it this way. I do define a node here, and now I want to copy this node. I go on move and copy. I create a copy 9.50 meters into Z direction, and I want to use the step links, which allows us to have a member defined automatically between the original node and the copy. Only I have to give here the settings for the member, so I create a new, and I want as member type, of course, to have the pile. For the member, we can see here in this register that our cross-section is assigned, and I want to have a look at the pile, and here the pile resistance type is assigned. We did define it before, so it automatically is found. Can say OK, and again OK, and then here we have our pile. So now the geometry is prepared. We have only to do one more step. We have to go into the soil solid. As the pile has to be integrated into the solid, we activate this option here, and we can see in the new register that we can here integrate objects. And we would have to integrate the line of the pile, so I can pick it here. Where is it? Here is it, line 17. It has to be integrated with an independent mesh. That's why I did put it on that side. We say OK, and now my pile is integrated into the solid. Then we can go on. We can start with the definition of the construction stages. So I do a right click here, and I can say new construction stage. Soil has a stiffness that is stress dependent and dependent of the load history, and these characteristics are resembled, or if an advanced soil material model is used, like the hardening soil, which is able to represent this behavior, it is required to use construction stages. So that's why we use it for the hardening soil, for having the deformation of high quality in the analysis for the soil. So the first stage is stage 1, and I would like to give it a name. It helps with having the overview on the phases. It's our initial phase. This is for calculating the stress from soil self-weight, so that we can afterwards use the correct stiffnesses. Here I have to assign the solids. I can activate the solids here, and I can set all. Then my soil solid is used. Then I also need to activate the surfaces in this step. I can also have a click here on all. They are needed here to have the surface supports of the soil massif considered. I click on apply, then it is in the model. I define the next construction stage. It's the near phase. For the hardening soil model, it is required to have in a first phase the material linear elastic, and in the second stage the hardening soil model is activated. So this means in this stage we don't need to change any of these objects. Now I create the next stage, and this is the stage where the pile is activated. I define pile activation, and I go here on members, and in members I can activate the pile. Okay, then we have it, and we can come to the last stage of this model. Here we want to assign the load, so I define it as loading, and we give it as OK, and we have the stages defined. Then we can go to load cases. We have the geometry defined, and we have assigned all the objects to the stages. Now we can come to the loads. I do go here, and maybe can go here to the base. We don't need to have the combination wizard in this model, and also this setting I don't need. We can go to load cases. We have the self-weight, and in Geotechnical Analysis add-on, this self-weight load case LC1 is the load case for the self-weight of the structure except of soil solids. And the second load case has action category permanent soil active, and it is the self-weight only for this soil solids. So I call it soil self-weight. Okay, and then we need one more load case, which is the loading. I will give it as permanent in post, and it is the loading. Okay. Then we can go to the design situations. I don't need them in this model, so I deactivate them. We can go to the construction stages. We are now here in this first step, and we can have a look at the load cases. And as we said, we want to use this, or we also need to use it for calculating the stress state of soil self-weight only. I go on apply, and I have my soil self-weight here. And in this stage, the material shall be considered as linearly elastic. So I can do this with activating a structure modification, and I define a new one. I don't need this setting here. I want to have the material's non-linearity deactivated, so I give a click here, and I also want to use the comment to have a better overview. I call it linearized material behavior, maybe. So we can click on OK, and then we can see also the comment here, and it helps. We can see now in stage 2, the structure modification is not active anymore, and here the full hardening soil model will be considered. In the load cases, we have soil self-weight, which is fine. Then we can come to the next stage where the pile is activated. Here we should, at least, I mean in the latest, we should here activate the self-weight of the pile too. And I would like to use a different static analysis setting. We click here and define the equilibrium for undeformed structure here. No, I mean not in this. We create a copy where we use the equilibrium for undeformed structure setting, and I want to use load increments and save results of all load increments. With this setting, the deformations are reset to 0, which means in my result I will not have the displacements from the previous construction stages. I will not have the displacements from the soil self-weight. We need to know the stress state to consider the right stiffnesses, but we don't need to know the displacements from the previous stages. That's why I use here this setting, and we change it here to this. Then we can come to the loading phase. We create another static analysis setting. Here I want to use a higher number of load increments. Let's consider 20. And I want to save results of all these load increments too. We go on OK, and I switch here to static analysis setting 5. And yeah, this is fine then. And I should activate the loading in the loads. Okay, then that's it. I say OK, and I have the load cases in the construction stages for the load side also considered, defined. Now we only have to put the loads. We have the load cases prepared, and we can see them here. We have the self-weight and the soil self-weight. They are calculated automatically. Only what we need here is in load case 3 to define a new nodal load. So I click here and assign it to this node. Say OK, and let's take 3,500 kilonewton. We say OK, and then this is fine. Okay, let's save it, and then we can control this model. I would like to check graphically the stages. We can see here now construction stage 1, and we can see that the soil solid is assigned in the next phase 2 or stage 2, then we can see in stage 3 the pile is considered, and in stage 4 also the load is considered, which is as wished. Okay, then that's it for us. Our model is prepared. We could start the calculation now, and I would like to show you here. We can go on calculate, and you can here calculate all or go on to calculate. I would like to show the calculate in cloud to you. You could click here, and in this dialog you could select the machine that you want to use for the cloud calculation. Let's use this one, and yeah, then you can say calculate in cloud. The model is uploaded, and you will get an email that your model was received and the calculation is started, and then later you will get an email that the model is solved and you can download it. And in the meantime you can go on working without any performance problems caused by a model calculated in the background. So yeah, this is an option you can use. In the PowerPoint slides that we will have available in the download, you can find a knowledge base article that I put there about the cloud calculation. This you can also find on the website for Dlubal Software. You can find literature on cloud calculation, some further information. Okay, so now I would like to show the calculated model to you. I bring the results to you. This one was also solved in the cloud, and now we can come to the result. Here we see the results, and this is the result of stage number 10. We can go here too. And yeah, you can see the deformation. It's the deformation in the results section. We will come to this later. We could also check the full solid, how it looks like, and yeah, this is the section. What I would like to show to you is our we need it for calibration. We now want to check the load displacement curve of that pile, and we want to compare it with the expected behavior, as the aim is to have a pile that resembles the behavior of that load test. So what we need is the load displacement curve, and for this we have a very good feature in Rfem, the calculation diagram. And we define a new calculation diagram. We have here the diagram type chained analysis diagram, and you can here this diagram type should be used if you use construction stages. So we can assign the last stage that shall be considered and the stage where the consideration shall start. And now we have to define the type of result for the horizontal axis, and we want to check the maximum deformation, and we can also here use UZ. And on the vertical axis I want to see the member's internal force, the normal force. We can select the member and the node of the pile head, and then our calculation diagram is prepared. You see we have more registers. We can here go to the diagram where you can see it better, and you can also use the settings here, get the values at these points, and you could also print this. You could print it to the printout report, or yeah, as you see. We here do have also the table with the values, and you can export it to Excel, and this is what we do. We export it to Excel. We agree, and now this is exported. I want to close it, and I want to show you the results. So this is the way you get it after the export, and I did create a diagram with that. I want to show you here. So this is actually it. We have the values from the program, and then I have also put it together with the reference curve, and we can see here this curve was the first one I received from this calculation we did prepare together. And the reference solution is here, the light blue, and we see that we are a bit far from that curve. We could model our pile with higher capacity with higher resistances, and this is what I did. In the next step, I did adjust the input for our pile so that I can come closer. We can see that here mainly the skin friction is leading. For getting this curve higher, we need to use a higher skin friction, and I did this in the next stage. I did use my table, and this was my default values. Then I went here, I did calculate the difference roundabout, and did calculate a new shaft friction value, and did calculate a new shear strength. So we had this before, and now we went with 60, and then it was close enough. So yeah, with this input value I did calculate it new. We can see here also. This is with you I did have the model of the first results, and here it's with the adjusted pile resistances. We can see here it did open up on my other screen. Here we can see that I did adjust the shear strength to be 60, and with that model I was close enough to my reference solution, and I know now with this input and with this hardening soil material that I did use in that model, I am quite close to my reference solution, and the requirements are satisfied, and with this input I could go into my main model for the LZ Bridge project, for the full model. Yeah, so we can see it as finished the calibration process. Okay, yeah, that's it for the first model, for our single pile model. This is what I did want to show. Now we can go to the next model, to the second part of this webinar. Therefore, I get this second model for us to here. Okay, this model I would like to use now with you. As we can see, we have here a bridge and a foundation for the bridge with deep foundation, and in this model this bridge is a graphical object. It's I did import it from our Dlubal blocks, and it is not active for calculation, but it could be of course activated, and you could have not only the foundation with the piles but also the bridge and the model and calculate the full model. So this is an advantage of our program. You can have the superstructure and the foundation together, and you could directly see the effects of a change in the superstructure on the soil, or change in the soil and its effect on the superstructure. So you can have the full model and can check the interactions directly. Okay, so this is the model we have here. We have construction stages used, and we can have a look at them graphically. We again have the initial phase there where the material is linear elastic. then we can come to the next stage where the near phase is happening. This means here we have the hardening soil model in this model 2, and here it is activated fully. Then we can come to the third stage where the piles are activated, and then here the slab and this surface are active, and then the loading comes. We can have a look at the loading. So this is the load of the upper structure, and the next step would be to have the bridge 2 and to have the load from there. Okay, these are the stages, and this model is already calculated, so we can have a look at the results now. I'd like to show this to you. This is the load combination for characteristic combination, and I would like to for characteristic design situation. Okay, so this is the deformation result. We can see the full deformation of the soil. And now we will have a look at results and at graphics, and I would like to print them with you into our printout report. That's why I would like to shortly introduce our printout report to you. We have here in the navigator for data at the bottom our printout reports, and there is one prepared. You could also create a new one here. I go on edit to show you the printout report manager. It looks like this when you create a new one too. Here you can select the items that shall be contained in the report, and we have here, for example, the materials, and we can activate here the specific soil material models. For example, here the hardening soil models. This one we don't use, we can deactivate. So yeah, you can select all things that you would like to display in that report. We have here the geotechnical settings, the load cases. Yeah, then we can say yes, save and show. Then it will be opened, and we can have a look at it. It again opened on my other screen. I take it here, I bring it here for you. Yes, this is our printout report, and this is what we have so far. We have an overview model and the tables that we selected. In this printout report you can edit the languages, you can add graphics, you can add text or headings. You can always remove parts, you can edit it and get more parts when you missed something like this. And we can keep this printout report open, so you can, that's an advantage also of this program, you now can go on working, and when you like a perspective, a view, a result, you can print it and directly check your report beside working here on the program. Okay, then we can go back to the results. We do see here now the displacement of the soil, and I would like to show a guide object we have to you. We have here the clipping planes, and I would like to create a new clipping plane. It should be placed in the pile position, and I would like to see the YZ plane. I can go here on OK and set active, and then my clipping plane is displayed, and with that clipping plane we can go through the model and check the behavior in the soil like this. And yeah, you can have a look at it, and we could also maybe as overview, as introduction, print it. And I would like to go here and cancel visibility mode so that we can also see our bridge. And yeah, like this we could, yeah, for example, this could be now print. We can go here on print graphics to print out report. You can also use your keys here that you defined. And now this graphic, we can see here preview, and I don't want to have the color panel here, and also I want to have a reduced height. We don't need the full page, so we go here on height and go on 50, and we can check it. It should be fine. Yes, I like it like this. I go on OK, and then it is print to our report. Then we can go on with checking the results. Another option to have a look into the soil. I want to edit the clipping plane, and no, I don't want to edit it. I want to switch it off, so I can go here and say clipping plane off. It's still there, and you could activate it later again, but for now we don't need it. I would like to show you the results section. We can click here and define a new one. I would like to go from here to here, so it's right through the soil solid, and then you get a result section here. It has to be activated in the results, then you can check it, and in this part of the navigator for results you can activate the result you want to see, and here in the part at the bottom you can change the settings for the way it shall be displayed, and we select the isobands. And what we can do also for the result sections is we can say that they shall be drawn in the foreground, so we can see them always. Yeah, I have more result sections prepared. I did create them the same way, and I did put them into the plane of the pile positions. And this I want to show to you. These result sections I did create, and they are here. Now I don't want to draw them in the foreground, so that we can see also the positions of the piles. So yeah, like this. And we have here in the navigator for display the option to activate the names of the result sections. And now I want to print this as an overview. I go here on print graphics, and Rfem kept in mind, let's say, the last setting, so now it uses the half page. And I want to have a custom name here, and we call it result section overview. Say OK, and now then it is print to the printout report. And now we can go on and just print the results. We can go to the first plane of the piles, and we need to have the control panel. Yeah, and then you can print this. Like this, we can say OK, and we can print this cross section, result section, then we can print this one, which is for this row of piles. And again with this, control panel, and we print this one too. And then we can also print the plane of the pile tip. And we can have a look on here, and we can go on wireframe model so that we don't see the model here. And we can also print the results in that zone. We say OK, and then we use the last cross section. Print this one, I now use Control and P to print. We say OK. So now we have a good overview on the soil results, and we can now check the piles. Therefore, we can activate here the member results. No, I want to have the global deformations. And in this control panel, you can switch off the solids and the surfaces. And what we have is then the members, and we can go to the object selection. I did prepare an object selection for the piles. We have here the results. Yeah, and we have an overview on the pile deformations in that model, and we can print this too. So Control and button P, and we can print it. You could, of course, again write user-defined names for these views. I only want to save the time now. Okay, so now we have documented all the deformations. We can stay with the piles and go to the inner forces. So we can go here, internal forces, and we can see them here. I want to switch off the results section names, and we have the inner forces here. And for having a better overview in the printout report, I want to create another object selection with view. For this, I select these piles, do a right click and say create object selection, and we can call it pile row short, as these piles are shorter, or any name you could give. And then in this control panel, you could use this object selection, and we want to only see the pile row, now this one. And we have here in the results for the piles, for the members, the option also to use it with colors. And now I want to print it like this, again to our printout report. So I again use Control and Print. And what we want to use now is our multi-print. For this, I deactivate this button, as I don't need to have refreshed images. It reduces the performance. So we go on multi-print here, and then these registers appear, and we can go through it. I don't want to have a new view on the model, and I don't need the load cases here. What I want to have print is the results, and I want to have these results: the normal force, the shear forces, and the moments. And I say OK. And now for this view, all of these results are print. And I have the other object selection prepared. We could do so also the same together, but I have it prepared and want to save the time. So we can now print this one. Use also the multi-print, and again uncheck these and check these, and we say OK. So now we have the inner forces print. Yeah, then I would like to show one more result. We can also look here, and you could also do a right click on each member in Rfem. You can always do this, and if you have a member, you have result diagrams for this member too, and there you get a detailed result along the length of that member. So we have here the normal force, and we could also print the inner forces in such a detailed way, and this we have here also the option to print it to printout report. And just as example, I would like to do this. We say OK, and it is print. And now let's go back, and I want to show you some soil stresses. Therefore we go here on solids, and I would like to show the principal stresses 3D. And we have to activate the solids again, as I had them deactivated. We go here, and we have a special type of display for solids that we want to use. And what we do see now is from this load combination that contains the characteristic loads for serviceability limit state, and it is the result, the stresses of all loads as final results. So what we have contained is also the stresses from self-weight of the soil, but we are now interested in the stresses that come from our project, from our construction, from our structure. And this result we can check here. If we change the type of results, we can see the differences to initial state as result. And this we do here. And we can go here. And now I can see the stresses and how they are transferred into the soil. And we can go here and we can check also. And we could use now the clipping planes again. I want to have it on, and I could go through the model and check where I have higher stresses, less stresses, how it is transferred to the soil. For example, this could be an overview image, and this can of course be print too. We can check it like this too. Yeah. I don't want to have the multi-print now. Current only is okay. I do print it, and the last result that I would like to show is the trajectories. We have them too. Yeah, and they also give a feeling for how the load is transferred into the soil, how the soil carries the foundation. And yeah, you could go through the model with moving this one. Yeah, and check how but let's go back to the full view, and you can also change the trajectories, the length of the arrows, and have a look at it. Yeah, okay, but this is it for now. I think we have an overview on which results can be displayed as an introduction. Of course, there's further options which can be checked in detail with more time. I would like to show the printout report that we did fill together. So we have here all the images we did, and I would like to go through it with you. We have here the results sections. We have the inner the pile deformations, and here the inner forces start, and we can see that the multi-print did work well, and so on. So this so far is our report. Okay, then yeah, that's it from my side. This is what I wanted to show you from the models. I would like to go back to our slides then to come to point 3 of this webinar. Let's go back to the slide. So now we can come to the next slide. Yes, so what are the next steps for us? We are now in the last steps of the 2D constraint modulus method or elastic half space method as option for the consideration of the soil. This means it will not be the full, if this option is used, it wouldn't be the 3D finite element analysis for the soil considered. There the soil would be considered as surface support, where the support coefficients are calculated in an iterative process with consideration of soil structure interaction. Then another topic we have in the last steps is the anchors. We will have the member type anchor, which allows us to model anchors as well. Then we are working on the soil stability analysis with phi-c reduction. This is the next step, and we are working on the chem-clay material model, which is valid for, as the name says, for clays and further materials. And then we will have also the model type 2D plane strain. So this is the projects we are working on mainly for Geotechnical Analysis add-on, and I did place them here in the right row. So the 2D constraint modulus method or elastic half space method and the member type anchor are the next steps, and the others will follow. Okay, that's it from my side. I would like to show you one more slide. Here we have the links I spoke about. We have here a link to cloud calculation, to a knowledge base article that provides further information, and I also did put a link to a webinar about the geotechnical analysis with construction stages and hardening soil material model, and the online manual for geotechnical analysis. So that's it from my side. I would like to thank you very much for your interest and participation, and I wish you much joy with our program, and see you the next time. I would like to give the word back to you, Andreas. Bye-bye.
Thank you, Juliane, for your nice presentation. As usual, I have an additional hint for you. Just book our online courses, the Rfem 6 masterclass course. This course is for beginners. Then there's also an Eurocode 2 and Eurocode 3 course. You can get more information by clicking on that button above at the bottom, or different buttons, or you can scan the QR codes. The courses consist of several chapters. You can stop the course anytime and continue when you have time again. As I said, just click on the buttons for more information. Okay, that should be also all from my side. I thank you for your attention. Thanks to Juliane for the nice presentation. Thanks to Alexander for the support by answering the questions. I wish all a nice rest of the day. Maybe we meet each other in the future webinar. Bye-bye.